In lesson 6.6, we're going to talk about more properties. So we'll start right off the bat here with our exponential equation. Now we've dealt with exponentials and we're looking at like a number to a power, but now we're going to put it in an equation. So something like y equals 5 to the x, or you might have like 27 equals 5 to the x. There's our exponential, and the equation has the equal sign. One concept we're going to use will make these problems pretty easy is any base, as long as your base is the same, the powers can be set equal. So let's take a look at one of these examples here. On example 1, our base is 1/2 and our base is 4. It doesn't look like they're the same base. But keep in mind that 2 to the -1 power is 1/2. And 2 squared is 4. So we actually have the same base. We could rewrite 1/2 as 2 to the -1 and then leave that power of x plus 7. We could set the other side as 2 squared to the power of 3x. Now, our bases are the same here. They're both with the 2's. But if we apply, remember, a power to a power, we would multiply. So we're going to actually multiply this through. That property said if we had b to the x, it would and b to the y, then x equals y. Since our b's or our bases are the same, we can apply our power rule, which would give us -x minus 7, and on this side 2 times 3 is 6x, and we can just set those powers equal to each other. And now we simply can add our x to both sides, and we would have -7 equals 7x. Divide by 7 on both sides, and -1 will equal x. So once we realize that we can create the same base for both of those, it makes our solving pretty quick. Let's try one more on the triad here. I've got 25. Remember, 25 is like 5 squared. And 5 to the 3rd is 125. So I'm going to leave their powers here. This was to the 3x, and this was to the x plus 2. By applying the power to a power rule, I would multiply and get 6x here and 3x plus 6 here. Now I'll continue to solve it like a regular equation. I can subtract 3x from this side and this side and get 3x equals 6. Of course, dividing by 3 on both sides, I get x equals 2. Won't do this whole one, but here, guys, remember this is actually 10. So if this was a 0 here, you'd have 10. It would go back 1, 2, 3, 4. So you might want to think of that as 10 to the -4. Just kind of a little bit different when it has a decimal there, but we can still think of it as a base 10. Now, with example 2, they're going to help us solve some of these. So at this point, there are other ways to solve this, but remember this is our base, so we might write that as our log base 4. Our number here is 17, and it equals the power of x. So if we did this and we decimalize that, we could find our same answer. There are a couple other ways that we can solve this, but for now, you'll find that we've done this before where you have an exponential and you turn it into a log. We've rewritten the equation as a log, and you would just type this into your calculator. In which case we would get about 2.04, I believe it is. Again, as mentioned in a previous example, you'll learn something about this later, but it is possible that this answer is the same as log of 17 over log of 4. It has to do with the change of base, but ironically, those are the same answers, and so we can stick to our exponential and logarithm conversion. Now, we can notice another property down here. If your bases are the same in the log, just like the exponentials, if your bases are the same and you're using log, your x and your y are equal as well. So if we looked at this example, let's look at example 5 quick here. Same for logs. I'm going to go to the triad first. Notice how I have log base 5 and then a log base 5 here. I can now set this equal to what the other side is. And if I do that, this is a quadratic, unfortunately, so I'm going to subtract the 4x from both sides. And that gives me x squared minus 4x minus 45 equals 0. If I factor this, that's x minus 9 and x plus 5. And I get 9, and -5. Now, it is important that you check again for extraneous solutions. That seems to never go away. So 9 is only going to be our answer because x equals -5. It's extraneous because if you plug -5 back into both of these x values, you get log base 5 of a negative number, and that is not possible. Now, the same thing will happen here on this top one. Even though it's not log, natural log still follows the rule. The same base is e on both of these. We don't have to write it. So I can simply set x squared minus 16 equal to 6x. Then, of course, I could subtract 6x from both sides. And I'd have to factor. You see, that's never gone away yet. X minus 8x plus 2. And my solution would be 8 and -2, but I would need to check those and plug them back into the equation to see which one of them would be extraneous and our -2 will not work. So this is our extraneous. If you put that in there, you get log of a negative number. This would be our only solution. Now, this example 3 I saved because we don't have the same bases. So I feel like the last two properties kind of went together. But if they don't have the same base, we're going to take the log of both sides. So this one would say log, if you log this side, this will bring your power out front. So if I have log of 3 to the x plus 1, and I have log of 5 to the x. Remember that power property when you have a log? What you do to one side, you do to the other. So we've logged both sides. But now, this power can come down by that power property. So I'd have x plus 1 out here, and I'd have log 3, and I'd have x and log 5. Now I'm going to get the logs on the same side here that have x's, but first I need to multiply this through here. So I'd have x log 3 plus log 3, because 1 times log 3 is just log 3, equals x log 5. Both of the terms that have x's now, I'm going to get on the same side. So I'm going to subtract x log 3 from both sides. So I would have log of 3 equals x log 5 minus x log 3. By having both the x's on the same side, I can factor that out of there, like suck that out of there, and I'd have log 5 minus log 3 equals log 3. And this isn't pretty, but it's going to work here. If I divide by log 5 minus log 3 on both sides, and this is all just a calculator number, I would have log 3 over log 5 minus log 3, which is not anything in our brain, not a number. It does come out to about 14.57, but that gives us our answer. It helps us separate that x. And note going back that when you have not like bases, you need to log both sides to bring that power down using the power rule. We just use our log base 10 to keep it easy. So in this next try it, you can check out your answer key, but if you log both sides, you'd have 3x times log of 2 and x plus 1 times log of 7. The problem would follow very similarly to this one in example 3.